Let's set the scene. We've got a brand new ice cream plant. The vats are chilling, the loading dock is freshly paved, and those first batches are ready to move. But before a single pint ships out the door, we need to ruthlessly interrogate the system. We're going to use failure modes and effects analysis, FMEA, to tear apart our own design and find out exactly how it's going to fail.
So the very first question you have to answer as an engineer actually isn't about the machinery at all. It's about the boundary of the problem. What is the single failure outcome we're trying to prevent here? For our new plant, we're scoping this strictly to one specific outcome: the product melting between the freezer and the store. Because, well, melting means heat exposure, bacterial risk, and ultimately ruined product.
Now, before we actually map this out, a quick structural note about the underlying logic. The methodology we're looking at works identically in both R and Python, exactly the same. So we won't be looking at any code syntax today. The math holds up perfectly regardless of your environment. Okay, here's the crucial thing. This analysis begins with scope, not just a list. You have to explicitly choose the process and that single failure outcome you're analyzing. I mean, think about it. If you just ask a room full of engineers, hey, what could go wrong in an ice cream plant? The list literally never ends. You'll just drown in hypotheticals. Scoping it directly to melting between freezer and store locks the analysis perfectly on target. So let's map out the components of this specific scoped process. We've got the freezer, the loading dock, and the truck. But, and this is absolutely vital, notice that workers are included as a component. People are components too. An FMEA that only looks at mechanical failures, it's usually going to completely miss the likeliest points of failure in any technological system. Right, so the block diagram is where the actual analysis happens. You don't just list out the components, you draw them as nodes and link them together in a sequence. Worker 1 puts ice cream in the freezer, worker 2 moves it to the truck, worker 3 drives the truck to the store. Once you draw those links, the failure modes appear precisely at the connections between them. A freezer breaking is one mode, sure, but a worker leaving a shipment on the hot dock, that's another. Okay, once we have our failure modes isolated at those links, every single mode gets 3 distinct judgment scores, and each of those is ranked from 1 to 10. First up is severity. If this happens, how bad is the effect? Say a freezer failure ruining days of product might be an 8. Second is occurrence. How often does this actually happen? A worker eating a pint on the job might be an 8, while a total freezer failure might just be a 2. And the third is detection. Now, this detection score is fascinating because it actually runs backward compared to what you might intuitively expect. You're scoring how likely you are to catch the failure before it escapes. A 10 does not mean perfect detection. Actually, scratch that. A 10 means you would almost certainly miss it. So a high detection score is terrible news because it means the failure is totally invisible until it hits the customer. Next, you just multiply these 3 scores together. Severity times occurrence times detection gives you your criticality index, which runs anywhere from 1 to 1,000. Now, looking at this mathematically, it is super tempting to assume that if you sum these numbers across all your failure nodes and divide them by the maximum possible score, it gives you a system-level probability of failure. But here is the critical mistake people make with this tool. The risk priority number, or RPN, is not an objective measurement. It's not a true probability. Adding up RPNs or dividing them by 1,000 tells you absolutely nothing about the mathematical chance that your system is going to fail. Its product is simply an ordinal ranking. It just sorts your failure modes from worst to least bad, so you know exactly what to fix first. Really, the numbers are just human judgment calls written down. The true value isn't precision at all. It's that they force a team's subjective disagreements right out into the open. By codifying these judgments into severity, occurrence, and detection, it makes those disagreements explicit, arguable, and rankable. It stops a team from just arguing in circles and forces everyone to debate the specific mechanisms. As you work through this conceptually, you really need to know what to look for in your results. A sensible analytical outcome pushes severe, frequent, and invisible failures right to the top of the pile. That's exactly what the multiplication is designed to surface. But a suspicious outcome? That's one where the top risks are purely mechanical and human error has been ignored entirely. If your highest risk is some 1 in a million compressor failure, but you haven't accounted for a worker just leaving a pallet on a hot loading dock, your analysis is failing. You have to evaluate your own blind spots. Look really closely at the judgments you've codified. Are your numbers hiding an assumption about how humans actually behave in your system? Watch your inputs, because a highly precise ranking built on flawed assumptions won't just fail to protect your product. It will confidently point you at exactly the wrong problem.